In chapter 5, we are going to apply Newton laws in more detail. We are going to use the free body diagram. We are going to show the forces acting on an object. We are going to also connect multiple objects together and use Hooke's law, which always want a spring. So we are stretching and compressing, so we are entering elastic forces. You remember the condition of equilibrium, all the x-axis forces, the forces acting on the x-axis down to 0, and the same for the forces acting on the y-axis. Quick recall, take a look to this example. We have a multiple object, an engine and a car. So in this free body diagram, we are going to discuss the forces acting on the engine, which is just suspended. So if this is just the x-axis with the positive x pointing that way, you will see that the tension 1 will be up in the cable, will be like that. And of course, there is a weight pointing straight toward the center of planet Earth. As for the free body diagram for ring O, let's recall what we have right here in ring O. So in ring O, you have a force called T2 pointing this direction. You see T2 right here. You have at an angle of 60, this is the angle, and this is a T3 right here. And if this is a 60 angle, this will be also 60. So it is a T3 having an angle that has the component, the cosine will be adjacent and the sine will be opposite. And of course, this will be T3 on the x-axis, and this one will be T3 on the y-axis. So basically, once we have all the components, all the forces visualized, we can apply the first condition equal to 0. So what do we have on the x-axis? Let's highlight it in yellow. We have this one, exactly here. And then you have a T2, which is negative because a point in the opposite direction of the positive x-axis. On the y-axis, I'm going to highlight it in green. You have a T3y right here. And then you have a T1 negative because a point downward. Don't forget to put them down to 0 and to solve those equations at the same time. Again, another example that you may find interesting and useful to refresh how it works is that we have an inclined plane at 15 degrees, that's your angle. This is your cart, is an object. Look at this tension in the cable. Yes, perpendicular to the surface, really to the surface is here 90 degrees, is the normal force pointing up, normal. This is a tension. And pointing down straight to prime is weight 1. Now at the very other end there is a second object, which is a bucket, which will have its own weight pointing down toward the center of the planet, and since there is a cable, again a tension in the cable. So what do we do with a multiple object? We have to do two different free body diagrams. The simple one is for the bucket right here, because of the tension and the weight, it's very easy to represent. As for the cart, here's the cart for free body diagram. Let me try to make it a little bit bigger. Let's highlight the normal force right here in green. Then you have the tension in the cable right here in blue, pointing toward the positive x-axis. Then you have, pay attention, the weight right there. So you see this weight will have an angle of 15 because of this inclined plane angle of 15. So this angle will be also 15. So the weight, as you can see, will have a component. This is a weight 1 component X, and this one, or this one, will be weight 1 component Y. So it's very important to do all the components so that we can proceed to more interesting equilibrium problem. Please pause, goes on chapter 5 and do on your own 1, 2, 3, 4 and 5. Simple acceleration, lifting an object, car on a ramp or inclined plane. And I like this one because it's a quick recall on 2-dimension equilibrium, and look at this one, 1-dimension equilibrium. See you in a few. Contact force and friction, we already discussed. An object has a frictional force that is always opposite to the motion of the body that maybe you pull or push. Yes, you remember the weight toward the center of our planet, and perpendicular 90 degree to surface is the normal force, which usually we use it pointing up, but it's just a convention. You can decide to do also the normal force pointing down. So it's very important to understand that friction will have 2 components. One is a kinetic friction, so the object is in motion, kinetic energy of motion, and the other one is going to be static. So basically these 2 frictional forces will be called the F with a small k for kinetic, and this one F with a small s, which will be equal to mu of k. This is the coefficient of kinetic friction. Is a coefficient, means it's very small number, usually between 0 and 1, a very small number, multiply the normal force. And your static friction will be exactly the same, coefficient of static friction multiply the normal force. Hey, by the way, don't forget the normal force equal mg. So very useful information, yes, to keep it on your summary. Here again from your book, but we already quantified, we already did it on our own, and this is the 2 types of frictional forces. Why is it important friction? Because the surface, every type of surface is not perfect, as always imperfection. It depends really on the magnification. You know, you think this surface, this point of contact between the floor and the block is smooth and frictionless. Actually no, if you zoom into, you will have this surface that is not smooth. So there is definitely friction. How do we quantify friction? We always have this coefficient of friction, again this elongated Greek letter mu, which will reveal how much force is involved. And again, it is a coefficient that is kinetic or coefficient that is static. But don't worry, it's just a number and is also a small number. Here another example to recall again a concept you are familiar. Someone is pulling on this object, a crate, at an angle of 30. And you see the angle is always computed counterclockwise from the x-axis. What are the forces acting on this man if we put him right there at the origin? Well, first, the main is really T. This is a great component, this is a tension. So if that is an angle of 30, this is an angle of 32. So this will be the component x of the force of the pulling of this man. Again, hypotenuse, cosine of the adjacent angle. And this will be T of y, again, hypotenuse, sine of the opposite angle, because this one is also T of y. tension along the y-axis. Perpendicular to the surface, you already know, is the normal force, and right here, you can see again the frictional force, kinetic frictional force, always opposite to motion. So this is a great free body diagram for a moving object, in this case a moving crate. How about this interesting example? Again, is an inclined plane and an angle called alpha. So how do we quantify? Well, perpendicular, we already know, is the normal force, 90 degrees, right here. Then there is a friction opposite to your motion, because you're sliding down this inclined plane. So this is a friction right there. You are moving, so it's a kinetic frictional force. And then you will have the weight. The weight is always pointing down right here. And if this is alpha, this is gonna be alpha also. So do you see that the weight has two components? Again, this is gonna be alpha, the weight on the x-axis, this component, which is also this one right there, right? It's opposite, indeed, the sign of alpha. And this one, you see, this is a positive y component, and this is a positive x-axis component, and this one will be component of the weight y, which is going to be negative because, again, points in the negative y-axis. So if we want to do the condition for equilibrium, you can easily come up with this equation. But don't worry, again, we are going to do a problem together. So you're going to see it step by step, how does it work. For the moment, I just want you to visualize these forces and do the free body diagram. In any case, you have a solved step-by-step example in the chapter about this one and how you get to this equation. We will do it again. We are almost done. Last type of force is an elastic force, also called Hooke's law. So again, there is a spring, and this spring is always quantified by coefficient, which we call small k. It quantifies the spring, the elongation, the compression, the material. So k is a very interesting coefficient. It's just a number. Now again, this is an object in equilibrium. Why? Because we put the position x equals 0. Now at this point, you can even stretch the spring, or you can double stretch it, or even, you see here, you compress it. When you compress, look, your displacement vector will become negative. So in general, we find that this Hooke's law, I like to write it down like this one, minus k, that's the spring coefficient, the spring constant, multiplied x, where x is nothing else than delta L, your displacement. So this is a Hooke's law, is always taken with the negative. But in general, there is also this force acting on a spring, which is a K delta L. But again, I like to write it down like this one, Kx, kind of much more easy. But it's exactly the same. It's all about an elastic force. Now pause the video because you have an interesting example to practice, that is 6, 7, 8, 9, 10, oh yes, 11, 12, 13, 14 and 15. Again, strong foundation so that we can do higher complexity problem together in a few seconds, because I have only 2 slides left to content. So you saw that physics quantify nature. Nature has forces with so many types already. Gravitational, electromagnetism, strong interaction, the force that keep this nucleus together. Weak interaction, the atoms that decay, radioactive decay. So all these four forces that are in nature, they are into one. Is what is going to call the unified field theory. I actually like to call it the toe theory, the theory of everything. And that's what we are trying, physicists, to unify these four forces, because at the very beginning of the universe, they were all in one. Again, study of physics is the study of the nature. All right, so may the mass times acceleration be with you. See you soon. Problem 5.4. We are still applying Newton's law. Look at this situation. You have two weights. One is 72 Newton, and I'm gonna call this one weight 1, and this one W2 is weight 2. Remember, weight is a force, so the weight is a vector, and the weight is mg. Mass multiply g, the very famous 980. So what we want to find is in a free body diagram. Then we are going to find the tension in cable A, B, and C. For the free body diagram, when you have 2 plus bodies, is to divide always in 2. So I'm going to do the first one for weight 1, and then I will do the second for weight 2. So weight 1, I'm going to place it right there in 0, 0 at the origin. This is weight 1. You will see that from weight 1 departs a cable, so a tension in the cable, T of C. Remember T, I'm going to put it right here, T for tension from now on. T of C is the tension in the cable. If this angle is 60, then also this angle will be 60, okay? So I show you with the highlighted. If this angle is 60, in light green, this angle is also 60, right there. The same apply for the tension in cable B, T of B. This is the cable B, right? The tension is right here, tension and tension. T of B is also, as you can see, at a 60-degree angle. So this free body diagram has a tension in cable C, in cable B, and absolutely pointing down on the y-axis the weight for body 1. So this is the free body diagram for weight 1. Great. Now let's move on to the second weight. Positive x, positive y, pointing up. Weight 2 is 150. I'm going to place it right there. So absolutely pointing down toward the center of Earth, you have the weight 2. And pointing upward is the tension in cable A. Nothing else for weight 2. Tension in cable A comes out from this cable right there in yellow. Okay? Let's move on. In part A, done. In part B, we want to find T of A, tension in cable A. So we want to look at Newton that says that the sum of all vertical forces must be equal AMY. Since the object is not flying off to space, is not taking off, this acceleration is 0. So we can use T of A, we can use this free body diagram, I'm going to call it with a star, and we can derive the first equation that says T of A is positive because it points up to the sky. Then I have the weight, it's down toward the center of Earth, so is a negative weight 2 equal 0. There is nothing else we can do except to conclude that tension A is equal to the weight 2. Wait a second, I know how much is weight 2 is 150 Newton. So I'm going to say elegantly T of A equal 150 Newton, frame it. In part C, we want to find tension B and tension in cable C. All the time you have two vectors at an angle, like T of B and T of C. I want you to break it down, so let's do a step at a time, okay? So I'm gonna visualize here for you, since we are still learning, right? This is a tension T of B, T of C, and this angle is 60. I'm gonna do the component. This one is a positive T of C on the x-axis, and this one will be a positive T of C on the y-axis. All right. It will be the tension in cable C multiply the cosine of 60. And for T, C, Y is going to be hypotenuse T of C. Since it is opposite, it will be the sine of 60. You know, if you prefer, you can even remove T of C right there, and I can add it right here if you prefer. So you can see that T of C, the tension in cable C, is your hypotenuse. I'm gonna do the same for the other cable. This is my convention for the Cartesian axis, and this is T of B. This angle, I know, is 60. Now look what happened. This is component X, positive or negative? Negative, because the positive x-axis is opposite. And this one will be component B on the Y, which you can also see. Since you see this is up is positive, so this one is positive also. Just a quick recall, you already know. All right, let's compute. T, B component on the x-axis will be the hypotenuse, which is a T of B. I know it's negative, multiply cosine of the adjacent angle. TB on the y-axis, yes, I know it's a positive, I'm going to put it in any case. If hypotenuse is a T of B, multiply the sine of the opposite angle. Okay? So again, a cosine here because it is adjacent, and for this one is the sine because it is opposite to the angle 60. Now, remember that now we have also x component. So Newton wants you to do the sum of all x forces, put it equal max. Since there is no acceleration on the x-axis, what we want to compute is this one. Frame it. You know, the object is standing still, there are two attached, they are not moving horizontally, and they're not even moving upward, you know, going to the moon or to Mars. So let's apply this condition. Now I'm gonna use the x component. I'm gonna highlight it in yellow. 1 and 2. Let's add them. Tc cosine of 60 minus Tb cosine of 60 equals 0. This is a constant. I'm not interested in carrying with me. So I obtain that T of C is equal exactly to the tension in cable B. Let's move on to the other knowledge from Newton, which is also equal to 0 because there is no vertical acceleration. So let's do that. I'm going to use a green, so I'm going to add this one to this one and few other weight, and I show you why. Let me write down in the meantime. I have a Tc sine of 60, right, plus Tb sine of 60. But if you look to the free body diagram there, you will see that where you have T of B and also T of C right here in blue, there is also a weight 1 to also is attached a weight 2. So those are component vertical that I need to keep in mind. Therefore, right here in this condition, I need to subtract the weight 1, which is right there, and also the weight 2. Now, finally, I can put it down to 0. So the condition that here I want you to pay attention are these two. Why? Because again, you are in this situation. On the vertical axis, there is a weight 1 and a weight 2. Both weights are downward, so negative. All right, let's keep on going in this case. If I apply this condition right here in the cloud, this T of B is equal to T of C. So here comes out twice T of C because of the condition I put in the cloud. Twice T of C sine of 60 minus, what was the weight of W1? Was 72 and the other one was 150 right there. So I'm going to subtract weight of 1, 72 Newton, minus 150 Newton. Elegantly, we are at the very end of this great problem, because this is an equation and I'm going to solve for T of C. Final answer is 128 Newton. Frame it. Since T of C is equal to T of B, is the condition I put in the cloud, Also T of B, 120 Newton, 128 Newton, problem done. In this problem, there is a car which is a mass of 1130 kilo and is being pulled up. The friction from now on, italic F equals 0 at a constant speed. The cable makes an angle of 31 degrees. Okay, 31 degree with ramp, but the inclined plane is 25 degree. We want to find a free body diagram. In B, we want to find the tension, T for tension of the cable, of course. And in C, how hard does the surface of the ramp push on the car? So I want to find the push on the car by the ramp. Yes, you have all the ingredients to make a great recipe with this problem. Let's do a free body diagram. I'm gonna draw on this drawing form. The best things I would like you to see is that this is artistic, okay? Then I'm gonna clean it up. I'm gonna place a y-axis like that and coincide with the inclined plane my x-axis. This is one of the best choice. So the cable will be put at the origin. This will be the angle of 31. What else? Well, the car will have a weight that points toward the center of the planet, definitely, which will be positioned here at the origin of the Cartesian system. If there was a friction, it would be right here, pointing opposite to the motion, but there is no friction. Good for us. The last force is that the surface of the ramp, again artistic rendition here, points up, push up perpendicularly 90 degrees. So this is the normal force, which I'm going to put it on the y-axis. All right, so let's clean it up. Yes, for the Cartesian, I'm going to rotate. It doesn't change really nothing. So positive y up. Okay, for the cable, I'm going to use a red ink. So this is a tensioning cable. The angle is 31. The weight in blue. Now, what's the angle? Well, from alternate angle flat geometry, if this is 25, as I explained to you during the theory, also this one is 25. And the last one is the normal force, which I'm going to put it here, N normal. As you can see, I'm going to do the components for T of C and the weight. So I'm going to write it here on the diagram. This is a T of C. On the x-axis is going to be the hypotenuse. Multiply the cosine of 31 positive. And this is going to be TCY, which is a T of C sine of 31 positive. When we look at the weight, you are going to see that actually right here is the right triangle. This will be the weight pointing down, you see on the negative. So it's going to be, the vertical component is going to be a negative, the hypotenuse, the weight, cosine of 25. And the x component, right here, I'm going to put it here. The weight x component also negative because it is into the x-axis negative. You see the positive right here. Since it points opposite is minus the weight opposite angle of 25 degrees. So we have our forces, the one at an angle into component. And it's very important at this point in the semester that you know how to do this component very well, because everything will be based on this one, okay? So make sure you study well with the video tutor, you listen to my problem. Physics is like going to the gym, repetition, repetition, repetition. And you can also even use YouTube, look up at other professors. But in any case, in Canvas, I added a lot of extra problem solved by other professors. So there is plenty of material, but components are really important. Probably you know by now. Let's apply what Newton says, that the sum of all horizontal forces equal max, the acceleration. Since there is a speed, so the object is moving, but this is a constant, you know that at constant speed there is no acceleration. The acceleration is a change of velocity over time. Since this velocity speed doesn't change, no acceleration. So this is really the Newton I am gonna apply in this case. Which are the x component? I'm gonna do it in yellow. Here is a x component and here's the other one. Only two, super easy. So I have Tc cosine 31 minus the weight sine of 25 equals 0. So as you can see, I can find this tension, I should call it just tension, by doing W sine of 25 divide cosine of 31. Wait a second, because I know what is the weight, which is only mg. So I'm gonna plug in mass g, and this sine, it's very easy to compute. The mass, I know it, you remember is given 1130 kilo, and how much is g is the very famous in absolute value 980. So if you plug in and you do the algebra, the tension in the cable will come out to be 5460 Newton. Final answer. So tension in the cable done. Let's go to part C. We want to find the push. So the push is in that red ink. So basically is the normal. We want to find the normal. So ask yourself, is the normal acting on x-axis? No. Is the normal along the y-axis? Yes. So let's apply Newton to that vertical axis. Again, the normal look is this one. You see, push up right there. So it's going to be the sum of all vertical equal 0, because we already discussed the acceleration is indeed 0. All right, let's do it. So you have a positive normal pointing up right here, look, right there in this green, positive, right? Then what do you have? A negative component of the weight and also a negative component of the tension in the cable. Let's use them all, highlighted. All right, so here it is, plus TC sine of 31, minus the weight, I put it in blue ink, equal 0. All right, so as you can see, we have everything, because a T of C, I found it out, is a 5460 Newton. The weight is a mg, right? So here you plug in the like before, the mass is 1130 kilo, and G is your positive. So basically, we can indeed solve this equation for the normal. So when you solve it, it will come out. I'm going to do a little bit of algebra. This one becomes negative, going on the other side of the equal. Sine of 31, the weight component y becomes positive. And if you do all the algebra and do so, the norma will come out 7220 Newton. Frame it, wait a second, this is the magnitude, and if I ask you the direction, is up or down? Indeed is up. Frame it, problem is done. This is a classical on the test, on the final. So remember, physics is like going to the gym, right? You're gonna do repetition, 16, set of 2. In problem 5.5, an archaeologist crosses 2 rocks cliff. There is a rope that is stretched in between. He stops to rest in the middle of the rope. The rope will break if the tension exceeds, it's more than this value in Newton, a force always in Newton. The hero, the archaeologist mass is 90 kilo. If we want to find in part A, if the angle theta is 10 degrees, find the tension in the rope. And let's do a free body diagram. All right, let's do that for part A. I'm going to show you first right here. I'm going to put the archaeologist at the center of the origin, plus y, and this one will be the x-axis. This is artistic take, then I'm going to clean it. So right here, I can visualize a force I'm going to call T, which is a tension, and here again a tension. If this angle is theta, also this angle right here will be theta. I also know there is a weight right at the center, right there, pointing down toward the center of our planet. So these are the 3 forces I want you to visualize in the free body diagram. Free body diagram. So I'm going to say tension here with an angle theta, the other tension here with an angle theta, and this is the weight, W for weight. What do we know? In part A, the conditions are very simple. We know that Newton says that the sum of all vertical forces equal MAY. You may wonder, wait a second, but what happened to all the horizontal forces? Well, since it's not accelerating, these are down to 0. So I really am going to focus on this one. The problem says that he stops, right? It holds halfway, means it's not moving. So it is not moving means that your acceleration, vertical, is suspended on this rope, is down to 0. So probably we can use at our advantage this information, because Newton's law becomes now very simple. Okay, so let's do that. First we should break into component the tension. My right triangle, and this one laying on the x-axis is a t of x, which will be given by the hypotenuse t multiply the cosine of the adjacent angle. Up here, here's the parallelogram, will be t of y, which is hypotenuse t sine of theta. All right, now for this one is going to be the same t of y, but this one will have a component right here that is a t of x. You see, it points opposite to the positive x-axis. Positive this way, but t of x points the other way, so I need to put a sign that is of minus. So will be the hypotenuse multiply the cosine of theta. Let's keep on going using Newton consideration. So what do I have on the y-axis? I have this equation here, right? Then this component. Then I have this component, and I'm going to make sure that we don't forget that this t will have also its own t of y, which is exactly the same t sine of theta. So 3 along the y-axis. 3 components of the force along this y-axis. The first will be t sine of theta, so I use this one. Then I'm going to add this other, again t sine of theta, and then the weight I need to subtract because it's down, so is negative, equal 0. Simple equation, I'm going to solve it for t, 2t sine of theta equal the weight, so the tension is the weight divided 2 sine of theta. At this point I can plug everything in, and I know everything. Why? Because I have the mass right there, up there. So what is the weight? Is mg. So at the numerator I have mg divided twice sine of theta. All right, let's plug in the numerical values so you are 100% sure that you're doing well. Mass g, absolute value, divided twice sine, and the angle was 10 degrees. So if you do the math, the tension will be 2.5 Newton. Frame it. Final answer. Quick recall that the Newton is nothing else than the kilo multiply meter over second square. Right. Let's move on to part B. Part B says, what is the smallest value of angle theta? So the rope will not break in half. So the smallest value of theta. So we want to find, right, this is one cliff, we want to find the smallest value with the vertical axis until the rope, here's the rope, here's hanging, will not break. So what is theta? Same consideration as we did before, nothing really changed, no acceleration, Newton, and as you can see, really this is the final consideration, which I'm gonna use it here. I know that 2 theta, 2 times the tension sine of theta equal the weight. I'm gonna solve it here for theta. All right, so the sine of theta will be the weight, which is mg, mass gravity, divided twice the tension, and the tension I have found it. So I'm going to do the inverse of the sine to find an angle of 0.01 degree. So it's a small angle, so it will be safe until this angle is like 1 degree. After that, it will really be dangerous and will break. In problem 519, as you can see, you have 2 weights, the weight A and the weight B, where weight A is 1 kilo and weight B is 3 kilo. They are attached to the ceiling, right, with a hook of the elevator. We want to find in part A a free body diagram. In B, we are going to find the tension in cable A, tension in cable B. When the elevator is not moving. And in part C, again the same T of A, big question mark T of B, when the elevator is moving down at 1.8 meter over second square. What is this value? Meter over second square, you know, is an acceleration. Wait a second. What does it mean down? Means is a negative sign, so I'm going to put it right there in red. Again, a quick recall, an acceleration is always measured in a meter over second square. Another quick recall, your velocity is always measured in meter per second. Your force, quick recall, is measured in Newton, W, Newton, N, sorry. Okay, so let's do the free body diagram. I'm going to do it here. So imagine that there are 2 bodies. So I'm going to do 2 free body diagram. Again, 2 bodies, 2 free body diagram. I'm going to start with object A. So here's my Cartesian axis. I'm going to place object A right here at the center. And what do I see? I see that there is a tension A right there, right here. Tension in cable A. I know there is the mass, so the weight of A, which is mg, pointing downward, right? So this is a minus mg. And right here, right at the center, will be the weight of A. Then there is also a cable B, right? Right there, cable B. So I have to add tension right there in cable B. So here it is, tension pointing downward, also negative of cable B. So this is a down, this is a down. How about object B? I'm gonna place B at the center of the Cartesian axis. I'm gonna do B in blue. What do you see? That pointing up in blue, you will have a tension B in the cable that is up. Then right here at the center of mass, there is the weight of B. Nothing else for object B. So again, pointing up, tension B, pointing down, the weight of B. So multiple object wants different, separate, independent free body diagram. All right, let's go on part B, where we want to find the T of A and the T of B. Tension A and B when the object is not moving. Ask yourself, is this action on the x-axis? No x-axis action involved here. So we need to use what Newton says, the sum of all vertical forces equal MAY. We know it's not moving, so this A of y is 0. So this is the equation I'm gonna plug in. Again, there are two objects, so I'm gonna do two different implementation of this important concept independently. So I'm gonna say for block B, if you look at the free body diagram for block B, I'm gonna do it in blue. Ink is gonna be a positive T of B, positive because it's up, minus the weight B, equal 0. So T of B equal weight B. The weight become positive going past the equal. So you remember the weight in general is mg. I'm gonna continue here. T of B equal mass B multiply G. And I'm gonna plug in directly. It was a 3 kilo and this is a 980 meter over second square. It is a downward, but you know the negative sign is right here, right? So we don't have to bring it again over there because I already included the negative sign. So T of B comes out to be 29.4 Newton Fremit. Now I'm going to reason for block A. For block A, I used the black ink, and as you can see, what do you have? Tension A is up, so positive. Tension B is down, minus the weight of A equal 0. So let's solve this one theoretical. So I have a T of A minus the T of B, and the weight here is a mass of A multiply G equal 0. So as you can see, you can plug in all the number. These become positive. So I'm going to plug in. This one, I know it was 29.4 Newton. The mass of A was 1 kilo. And G is a 980. So if you do the math, for tension B, you will have a final answer of, let me write it down like this one, 4 10 to the 1 Newton Fremit. Let's move on part C. This is when we want to find TB, T of A and T of B, when it's moving down at, you remember the acceleration of 180 meter per second square, but the down I have to put it as a negative. So as you can see, I'm going to really recycle the condition we did, except that now has to be equal to m of y. All right? So again, for block B, what I'm going to do is to take this equation right here, and I'm going to plug it equal to m acceleration. All right, let's do it. I'm going to use blue ink so you remember where it comes from. It's going to be T of B minus weight of B equal now mass of B A of Y. So this is the, because there is an acceleration that is downward. All right, I'm going to continue. T of B equal MBAY plus WB. Look how elegant is physics. I'm going to continue here. Mass of B and the downward acceleration plus the weight, and this is the weight. So the weight of B again is m of B and G. And the negative is already been computed, right? Is an acceleration of gravity downward. That's why there is a minus there. So T of B, I can also group m of B. So A of Y plus G. All right, let's continue right here. Mass of B was 3 kilo. Then I'm going to open a square bracket so I can plug in the very famous negative 1.8 given by the problem. Close parentheses, plus G, that is 980. So if you do the math, it will come out 24 Newton, frame it. And do the math on your calculator, because you become faster and faster, and you also gain self-esteem and self-assurance because you feel solid in your algebra. Let's do block A. Block A again is gonna be this equation, this knowledge right here. Except that this one will be equal to the mass and the downward acceleration. Let's import that. It was plus T of A, right? This one. Minus T of B minus the weight of A equal mass of A multiply this A of Y. That is the downward acceleration right here, negative 1.8. I'm going to solve it a little bit theoretically so you can see how interesting and how elegant is this equation. So tension of A will be T of B. The weight of A will be positive going past the equal, and this one stays here. Now you do remember that the weight of A is m of A multiply G plus m of A multiply A of Y. So this is again very elegant. I'm going to group m of A like I did above, and you have a G plus A of Y. Let's plug in and see what happened with this equation. Don't forget A of Y is down minus 1.8 meter per second square. So T of A will be, T of B was 24 Newton, right here where I put the star. Mass of A was 1 kilo. Then I'm going to open my square bracket, 980, acceleration, plus here's where I put my negative value. So if you do the math, we are almost done. The tension in cable A will come out to be 32 Newton, frame it. Very interesting problem. This is a 513. We want to find the tension in each cable. So in configuration A, I want to find the tension of A, tension of B, and tension of C if the weight is suspended is 250 Newton. So in configuration A, you see immediately that there is a tension T of C in cable C, and this is nothing else really than 250 Newton, so that was kind of easy. Then there is a tension B right there. I'm gonna do in red, and here is again tension A. And we want, of course, compute all of them right here at the origin, or where there is a focus, or where there is a ring. So let's do a free body diagram. For part A, as you can see, it's kind of interesting and kind of easy. T of B is this one in red ink. If this angle is 45, also this angle will be 45. T of A is like that. Again, I'm not in scale. And the angle of 30, if it's here, will be an angle of 30 also here. But you can also see it, for instance, this way. You can also compute this right triangle, and you can use this angle right here that is also 45 degrees. The same here. You can compute this angle right here that will be 30 degrees. So whatever you prefer, it's going to be exactly the same. There is one more weight, let's not forget it, that is downward, and this one is the weight given by the object, that is 250 Newton, pointing downward. Okay? So this is the situation. As you can see, we need to compute all different components. So I'm going to do it here for you. In red, right here, this one will be component T of B on the vertical axis, which want the hypotenuse, sine of 45 degree opposite angle. This one will be my x component. This one will be my TBX, which is also this one, put it very elegantly, right? X component on the x-axis. And TB of x wants the hypotenuse, tension in cable B. Since it is adjacent, I'm going to put cosine of 45. They are both positive component pointing up toward the positive y-axis, pointing right to my positive x-axis. Let's reason on the component in blue. So here will be pointing up in blue will be your T of A along the y-axis, which will be the hypotenuse T of A. Since it's opposite to the angle, I'm going to do the sine of 30. Let me erase this one. I like to be neat. So again, T of y, this component right here, wants the sine of 30 because it is opposite. This will be T of x, you see, which is also down here. This is the component of tension A on the x-axis. Immediately you see you points in the negative x. So for component of tension A on the x-axis, there is a negative. Hypotenuse, T of A, since it is adjacent, you see, this is adjacent to the angle, I'm going to do the cosine of 30 degrees. So I have all components, now I can move on to find each component. Now the object is not moving, so there is no acceleration on the x, and is not even falling down, so the acceleration on the y is 0. So Newton says apply this condition, right? Condition of equilibrium. Let's do it. Let's see if we can find the x component. One is here, the other one is here, and done. No, nothing else. There are no other x component. So here is a TB cosine of 45 minus T of A cosine of 30 equals 0. So out of this equation, I can compute, for instance, T of B. And this one will come out to be, okay, come out to be T of A cosine of 30, and cosine of 45 will be at the denominator. So this one comes out to be a small number, 1225 T of A. And I am really locked here. So I can do anything else. I have this condition. I have two variables. T of A, you see, is a function of T of B. They are related. Let's see what I can do for the condition of equilibrium for the y-axis. So what do I have vertically? Well, for sure, this one, which I know is a negative because it's a pointing down. I have also this one, y component, and this one. All right, let's do it. Let's start with TB, sine of 45. Then in blue ink, minus T of A, cosine of 30, and then minus, I would say the weight, I'm going to just plug it in, minus 250 Newton equal 0. Okay. Well, we are kind of lucky because I know that T of B is dependent on T of A. So I'm going to plug this condition right here. So right here, where is T of B? Let's do it. 1 T of A, this is the condition. Then multiply will be the sine of 45 minus T of A cosine of 30 minus 250 Newton equals 0. So this is an easy equation. There is only one unknown parameter, that is a T of A. So if you do the math, T of A will come out to be 183 Newton. Now I can easily solve, right, also this one, because T of B will be 1225 multiplied 183 Newton. So T of B final answer will be 224 Newton, frame it. All right, so for this configuration A, I think we did great and we are in good shape. Do you agree? Okay. So let me now reason on the other configuration in part B. Let me show you again. This is the wall and the ceiling. You have a cable A that has an angle of 60. Cable C, which has the weight, the very famous 250 Newton. And then there is a cable that goes 45 degrees to the ceiling, and that is a cable B. So we want to find the tension in each of that cable. All right, let's do a free body diagram. So I'm going to move it up. So here's I have my Cartesian axis, positive y-axis up, and this positive x-axis. T of B, I put it, what was it, in red ink, so let me do the same. So this is a T of B, right here, T of B. This will be corresponding to the line of the ceiling, and this is the angle of 45 degrees. Let's do component right away. So this will be TB of x, and this one also will be TB of x, which want the hypotenuse of T of B cosine of the adjacent angle. This is a T of y, right? TB of the vertical axis, which is also this one. So I'm going to place it here. TB of y will be the hypotenuse, tension in cable B, multiply the sine of 45 because it's opposite angle. Let's do T of A. T of A is right here, right? So this center, this knot will be right there. So T of A, I'm not in scale, will be like that. This is T of A. And I know that this angle right here, let's say with the wall will be 60 degrees. So we can use it, we can use this triangle, right? Right there. So here you can see you have a T of A on the x component, which point opposite. So this is a negative. What do you have? The hypotenuse T of A, and then you have the sine of 60 because it is opposite to the angle. Look at this y component, which is also this one right there. Okay, so this y component of tension A will be negative 2 because it is opposite, right, pointing down. So that's why I put a sign minus. Also this one is negative, this one is negative. Will be the hypotenuse, which is a T of A, right, the hypotenuse. Adjacent angle, it's a cosine of 60. Now there is also another one in green here that is the tension in cable C, which is the weight, which is again 250 Newton. I'm going to put it right here in green, right there, and that is T of C, which I already computed, 250 Newton, frame it, which is the weight given by the problem. With this condition, we can, again, like we did before, apply all we know. Now, as you can see, we are gonna use, like we did here, the same condition, the object in equilibrium on the x and on the y axis. So I'm going to import those concepts, sum of all the x equals 0, and here I'm going to do sum of all the vertical component equals 0. All right. Let's do in yellow, the x component, TB of x, tension A, x component, and that's it. Let's do the math. I have TB cosine of 15 minus T of A sine of 60 equal 0. So like I did above, T of B comes out 1.225 times the tension in cable A. Now let's look for the Y component, here in green, 1, 2, and 3. All right, let's import them with the sign. In red is a TB, sine of 45. In blue, minus TA, sine of 60. Wait, I'm not done. And then, this is also a negative pointing down, minus 250 Newton equals 0. Exactly like we did before. You remember this heart shape is a T of B. So I'm gonna plug in and the rest stays the same. And if you solve for T of A, it will be 683 Newton. And again, do the algebra on your own. At this point, I plug it over there, and I will derive that T of B comes out to be 837 Newton. Frame it. So very interesting problem. Hope you enjoyed it.
Physics. Hyperbeam galaxies. Planetary nebula. Supernova.